This old Strobotuner from the 70s isn't working and needs some maintenance. Let's see if we can get it restored to working order. The CONN ST-11 is a musical instrument tuner that uses an optical illusion called the stroboscopic effect to tell when the pitch of a note picked up by the microphone input is in tune with the note chosen on a selector switch. So we have C, C sharp, D, and so on all the way up through the scale to B, and then we just start over at C. So if you're tuning something like a guitar string or a piano where you know what note you're expecting, you put that note on the selector switch. Then when the microphone picks up a sound, right now the unit is off, but when it's on, this disc in behind here is spinning, so this kind of looks like a blur. But as you tune the instrument, when the audio frequency gets near the expected musical note, you'll see a certain region out of all of this looking like it's actually standing still or maybe slightly moving. And that indicates the instrument is in tune with this note. So to explain the stroboscopic effect, imagine if this is a strobe light and it's dark and this is blinking at a certain rate. So let's say an object is starting to appear. You turn on and then turn off the strobe light, so you see it right here. But this is continuously moving, so it travels to here and the strobe light comes on and off, and strobe light comes on and off. So you see a jolting movement in the strobe lights. In this case, we have this disc constantly rotating with this pattern on it. So suppose it's all set up so that this is constantly rotating, and every time it's in this vertical position, the backlight comes on and goes off. And this is constantly rotating, so now everything is dark. It's vertical again, so the light comes on and goes off. And this is going so fast, and the light is blinking so fast, it just looks like it's always on, but you're only seeing this object every time it's vertical. So this is rotating, but you're seeing it just as always vertical, and that's the stroboscopic effect. So this is set up where you choose a note. In this case, it's on note C. So that will make this disc spin at a certain rate so that if you have a microphone picking up musical notes, when you get note C on the microphone, the audio is controlling the blinking rate of the lights behind here. And when they match, the image will appear to just be stationary. But if the note is slightly out of pitch, maybe at some point the light will come on when the image is vertical, but when the note is controlling the blink rate, maybe the next time the light comes on, based on the audio frequency, it'll be in this position. Then the light goes off, you keep rotating, and the next time the light comes on, it's in this position. So you see something maybe go from here to here to here, so the image is jittering all over the place and you know you're not in tune. So inside that test equipment, we have an oscillator, and then we have a clock divider which can slow down the pulses from this oscillator based on a selector switch, which is this one to control what note we are tuning to. So ultimately we're going to get an adjustable frequency pulse out of here, and that's going to a motor driver for a synchronous motor which has this rotating disc on it with a certain pattern. So we choose what note to tune to, and the motor is going to spin this pattern at a different rate. Behind the disc, we have 3 neon bulbs. So there's a neon bulb driver, and controlling this driver, we have the audio input signal going through a signal conditioning amplifier circuit. And based on the frequency of the incoming audio, it will cause these neon bulbs to turn on and off at a certain rate based on the frequency, and that makes this pattern on the display either stand still if you're in tune or rotate at a different speed, indicating if the frequency is a bit high, a bit low, or not even close to what you're trying to tune to. So we have a gain control here, which is adjusted based on the signal level of what we have plugged in. You may need to turn this amplifier up, or if the signal is too strong, you turn the amplifier down. And we can control the main function here. It's an off switch, or it can go to calibrate mode, normal mode, or +2 octaves mode. So we'll look at those. But where we're having a problem is in the calibration mode right now. And the fourth knob is called cents, where a cent is 1/100th of a semitone, or 1/100th of the difference in pitch from one key on a piano to the very next key, another semitone away. So two notes side by side on the piano have their pitches separated by 100 cents. And we can calibrate this unit by basically speeding up or slowing down the motor slightly every time we power on, so that the unit is always calibrated and ready to go. And it uses the AC 60 Hz frequency as an assumed reliable reference when it's in calibration mode. So when this is plugged in, we should be able to put it in calibration mode and adjust, if necessary, the sense control until we get a stationary image. But that's where I'm having trouble with this unit. The knob feels a little rough, and it's probably dirty from over 40 years of dirt. So I'm guessing maybe this is not allowing us to get a stable oscillator frequency to run the motor at a consistent rate. So maybe cleaning that will help. Or else, if this is all okay and we have a steady oscillator, maybe there's something wrong with the motor driver circuit. Maybe there's old capacitors, or maybe the motor is seizing a little. Now that I took this apart, inside we've got our power transformer and a few capacitors, and this is the synchronous motor for the display, and it has a couple of capacitors associated with the circuit there for the driver. There are circuit boards in a few places. This one here has a matrix of a bunch of diodes, and here are 6 dual JK flip-flop chips, 7476, and some other components in there. So this basically is a clock divider from a main oscillator, which is over here, and based on how it's set to run, it'll control the speed of the motor to get the stroboscopic effect to work with an audio signal. And this circuit board here has 2 74121 monostable multivibrators, and they are configured to make an oscillator free running. So we'll look at the schematic, but to get started, down at the bottom of the unit, I had access to the switches and potentiometer on the control panel, so I sprayed contact cleaner into wherever I could and moved all the contacts or the potentiometer to exercise it and help it clean. And it's already working a lot better. Now I can run it and calibrate it instead of having it constantly drift. So I think the calibrate potentiometer was dirty and the resistance wasn't consistent, so we couldn't get a consistent motor speed. Otherwise, just looking around with parts all over the place, like this fuse floating in the air, going directly from the power switch over to this contact, capacitors here and there, circuit boards. Just doing a brief visual inspection, I didn't see anything immediately, like any leaking or obvious bulging capacitors. Maybe I'll see them as I keep looking. But for now, I would like to just try to get the unit running, and I don't want to mess with anything that doesn't need to be messed with because I could break something. And here's the schematic, so we'll have to zoom in. We have AC in going to the power transformer, which has 3 windings, so it looks like we have a plus 180 volt supply here. And this winding is a low voltage one where it looks like they are deriving 5 volts regulated. And then we have this other supply up here giving us plus 50 volts for the motor. So this is our 5 volts for any digital logic and also to power the pilot LED. But before the DC part, there's a full wave rectifying of the AC, and that's going off to the calibration part of the circuit. So that can be switched into everything else to calibrate based on the 60 Hz AC power, assuming that to be a relatively reliable calibration standard frequency. So we're actually working with 120 Hz as our test signal because we're taking both halves of the sine wave with these diodes. The 180 volts is going over to power the neon lamps that are behind the rotating image on the motor. And these lights are turned on and modulated based on whatever frequency of signal is coming in, whether it's from this AC calibration on the switch or from the audio amplifier taking the test input audio. So basically the lights behind the image will blink at a rate based on the frequency being used, and if the motor is running at a certain speed where the test signal is flashing those neon lamps at the correct rate, we'll get the stroboscopic effect making the image stand still, and we know that we are tuned correctly. So this is our audio input signal, and it's going to basically a transistor amplifier, and we're running at 12 volts. We have our 50 volts for the motor up here, and aside from powering the motor, we are tapping into it, and with this resistor and this 12 volt Zener diode here, we're creating a 12 volt power rail for this amplifier, and the audio comes out and goes to that selector switch, so when we're not in calibrate mode, we can channel the input test audio over to the neon lights, and they will blink at a rate based on the incoming audio. At the same time, that audio goes into another transistor circuit here. This one's powered at 5 volts. We're cascading this audio signal at a 5 volt level through 2 flip-flops. So we're dividing the incoming frequency by 2 and then by 2 again. And every time we divide by 2, we lower the signal by 1 octave in terms of music frequencies. So we have this other signal that's 2 octaves below the original audio, and that can also be selected as a +2 mode on the switch. And we'll look at how that works later, but for now that's this whole network here. So in summary of all of this, these lights here have to blink at a certain rate, matching the speed of a motor to get the stroboscopic effect. So we control the blinking of these neon lamps with the mode switch in calibrate mode, taking the AC reference signal at a known frequency, or the audio coming in at a certain frequency, or a version of the audio 2 octaves lower. The motor is a synchronous motor at 50 volts, and there's a transistor driver here, and the speed of the motor is controlled by this transistor here, receiving a clock pulse from all of this. So we have a master oscillator, then we can slow it down with a 12-stage binary ripple counter, and we have this diode matrix here where we can preset numbers on this counter and control how long it takes to complete a count cycle and generate a new output pulse. So we're using this basically to control the speed of the motor by turning this transistor on and off at different rates. The part numbers for things like the chips and the transistors are in a separate list in the manual for this, but these are 2 monostable multivibrators or one-shot pulse generators, 74121. So based on timing, resistors, and capacitors, when you trigger an input, you cause one single pulse to occur at a certain width, and then it just stays low until triggered again. So they're using 2 of these, and one output is triggering the input of the other, then the output of that one is triggering this one again. So once it's running, you get a pulse, and then it continues. But in order to get this started, we need an initial condition, because when we power up, we can't guarantee that we're going to get one or the other of these actually doing anything that will trigger it. So looking at the 74121 datasheet, basically we're looking right now at what conditions do we need on this monostable chip to generate a pulse out. So we have 2 A inputs and 1 B input on each chip. And the pins are not labeled here, but these 2 are the 2 A inputs on each chip, and they are tied in common. So both A are always going to be the same on a given chip. And this pin here is B on each chip. So on this one, B is always pulled to, this is the +5 rail. So on this one, B is always high, and we need to know what can we do then on the A inputs to trigger a pulse. So I highlighted these 3 possibilities where B is going to always be high. We can get a pulse triggered if we get a falling edge on the A inputs, because you could get a falling edge on either one of them and it would also trigger, but we have them tied in common. So this case here, when A1 and A2 go from high to low while B is always high, we get a pulse. So we need this part here to go from high to low, and we can generate an output pulse. But this is tied directly to the output of this circuit. So now we got to figure out, how do we get a pulse out of this one, because that's what's going to cause a pulse over here. In this case, the two A inputs are connected to the output of this one over here. So the B input over here is pulled high, but it also has a transistor that can connect it to ground. So if we can assume that at some point after power on, this output here is going to go low, then we can say the two A inputs will be low, and we're waiting for something to happen on B to kick off a pulse. Because in the datasheet, we're either going to have the Q output being low, or it's going to momentarily be high and then go low until triggered again. So if we say that one chip has the two A inputs connected to the output of the other chip, and it's going to be low after everything stabilizes at power on. If either one of these are low, and we have them tied together so both are low, in order to generate a pulse on that first chip, we just need the B input to have a rising edge. So here, B is going to already be high on power on, and everything is going to stabilize, and then the inputs are going to be ready to see a rising edge. So we need a way to bring this B input low and then release it so it can be pulled high again and kickstart everything. So on this transistor, when this is on, the B input is pulled low. So here we have a 10K to ground, and I think it's a 10 micro to 5 volts. So when we first power on, before this capacitor charges, we're going to see some voltage level at this junction here, and then as the capacitor continues charging up, that voltage is going to drop because we have this 10K to ground and a capacitor that's eventually going to charge and then block DC, so we would only have a pull down, turning the transistor back off. So we power on, we should get a certain voltage, and then it should drop. So it turns this transistor on, bringing B to ground, and then the transistor is released. So B starts going high with this pull-up, and that's the rising edge, with these two inputs being low, from this output being low when it is in steady state waiting to be triggered. And we end up triggering a pulse here. So we get a high and then a low, and again over here, B is always pulled high. So we get a high and then a low, so a falling edge. We trigger a pulse over here. So now on these A inputs, we're going to see a high and then a low. So the thing keeps going and generates an output clock here. Now that goes into a string of 12 JK flip-flops. Here's an example from All About Circuits. We have some JK flip-flops, and the Q bar is used at the output of one to clock the next one. And then you could use these Q bar outputs as your counter output. So then, unlike the usual up counter where you start at all zeros and you count up, using Q bar, you start at all ones and you're actually counting down. And just glancing at the 7476 JK flip-flop datasheet, these have a preset and a clear. So asynchronously, you can set a Q or a Q bar output either high or low. Then when you release that override, it'll go back to responding to the clock. So here the main oscillator is clocking those flip-flops with the Q bar outputs feeding each stage. And these diodes are all hooked up to pin 3 or 8 on each dual flip-flop chip. So 3 and 8 are the clear pins on the two flip-flops, and clear is active low. So when you bring that low, Q is low and Q bar is high. So all we need to really get out of that is the oscillator is running at a certain rate. This counter is always going to count down to 0, but periodically, if we use these diodes, we can preset a number here and it will just count down from that number. So by setting different numbers, we can count down to 0 at different rates, generating a different final output clock rate, which runs the motor at a certain speed to make the system work with these neon lamps flashing at a certain rate. So this ties into the setting of our mode switch, whether we're in calibrate mode or looking for a certain musical note, which corresponds to a certain frequency and a certain motor speed. Using diodes, we're setting certain inputs low at a certain point in this whole count cycle so that everything runs at a certain clock rate to run the motor at the right speed to pick up the certain notes and tell us that we've locked onto it. So it's a bit of asynchronous chaos, but that's the overview of what's happening. Right now the unit is turned off and there's nothing triggered on the scope screen. I have it set up to trigger on an event when I turn this on. So I'm probing the A inputs on both monostable circuits so I can see the train of pulses where one output triggers the other input and then that output triggers the other inputs. So I want to see this behavior, and since this is all initiated by this transistor, I'm probing the base here at the junction of this charging capacitor and this 10K to ground so I can see when I power on what happens and how this all fires up. And because this clocks the string of flip-flops, I'm also probing the test point at the output at the end of this string of flip-flops so I can essentially see the end result of dividing this clock down, and that's what controls the motor speed. So I'm going to turn this on and it's in calibrate mode. So that's our power on startup sequence. I'll try to zoom in. So the top blue trace is at the transistor for the power on capacitor charging. So the top trace probing right here. This capacitor is allowing this junction to charge up to around 3.5 volts. And then as the capacitor charges and we start blocking DC, this will fall again. And that gives us our power on trigger to kick things in motion. Then the next signals on the scope. Below the capacitor, we're looking at these A inputs. Below that, we're looking at these A inputs. And the very bottom, we're looking at our final oscillator clock output. So if I try to zoom in on the traces, this is the power on where the capacitor charges and triggers the transistor with a couple of glitches to get the first monostable to generate an output single pulse. So the capacitor has been charging and the transistor base is going back to a pull down to ground. And here's where things start. So we can see the first monostable to generate an output is the one that the transistor is connected to. So that transistor initiates this first pulse, and then when this pulse is done and the signal goes low, that triggers the other input on the other one shot. So they each generate a single pulse, but they keep triggering each other. And at this point, we have started clocking the binary counter, so we're waiting for something to happen at the final output. So there it is, just free running in calibrate mode. The base of that transistor is low, and when I zoom in to see those two one-shot pulse generators, it looks like after the circuit has stabilized, those are also more even with the on-time and off-time. So now just taking another power cycle, the capacitor triggers the transistor to kick the one-shots into continuous re-triggering. When we zoom in on the first section of this, so when it starts out, it does do a couple of bursts, but then it goes more consistent. There's a tiny gap here, and then it just looks like it's free running a lot easier. So now if I put it into the normal tuning mode and looking at the pulse train on the bottom, which controls the motor speed, right now it's set to look for note C, which is going to be the lowest frequency. And if I switch to look for note B, that's the highest frequency, so that will change the motor speed to run accordingly. Then the stroboscopic effect will allow the image to stand still when the right frequency is detected. Now that the unit has been cleaned, I just want to test it, so I'm going to put it in calibrate mode. And the manual says give it about 1 minute to warm up, and then it should be fine for this power on. And now, because the image is rotating, I'm going to turn the sense dial and try to get it stationary. or slightly moving. So zooming in, when we're in calibrate mode, out of these markings on the window, we're looking for the number 2 section, which is this dark line here that's slowly drifting. Everything else on that pattern is a blur right now because we're not getting a stroboscopic effect, but we are locking onto this stationary almost image in area 2, and I will put it into normal mode. Now it's only going to get a light when it hears audio like me talking. I have a microphone here, and I'm using this keyboard. So right here on the keyboard is middle C or C4. So when we play note C, I have it set for note C on here. First, if I just go to a different note, the display lights up, but we don't see any locked on dark pattern. So if I hit C4, because we are looking for note C, now we have a pattern in the 4 section of the window. So we're looking for note C, and we're looking for the number 4, C4, for this pitch. And there's other areas that might look like they are locking on because we might be picking up overtones in this synthesizer, but we are picking up C4. Now if I go an octave up, this is another C, but it should be C5, and on number 5 in the window, that's where we are locking onto the pattern. And up here, if I go to the very highest C note, it should be C6, and we're locking on in area 6. As we get to these finer lines, sometimes it can be hard to see, so that's why there's a selector switch for +2. So now I'm in +2 mode, and I was looking for C6, but I'm basically scaling it down so I can see it on these thicker lines a lot easier. So I will count down by 2, so instead of 6, I should see it in area 4. If I go back to normal. So that's basically how the Strobotuner works, and using different parts of the display to get different parts of the optical illusion to look stationary based on the note and the actual octave of the note. The problem with a synthesizer, though, because it's not as pure of a tone, in this case I'm having trouble getting lower octaves, so if I go back to middle C, that's in the 4 because it's C4. But if I go down an octave, it should be C3, but I have to kind of hold the note and wait for it to ring out and get rid of some overtones, and then I can see in area 3, it's a C3. So as long as we know how this generally works and how to interpret what we're seeing, it can be a very accurate way to tune.